Okay, so we continue our discussion on the ideal fluids, and in this lecture we will mostly discuss some interesting properties of ideal fluid equations. So basically, as you can see that again this A, B and C, these three equations are nothing but the continuity equation, the momentum evolution equation and the energy equation for ideal fluids. Okay, that is for just recapitulation purpose. Okay, so now you will just to see that we have 5 equations and we have 5 unknowns, rho, v and epsilon. All the p is there, but we know that rho, p and v, they can simply be written in terms of effectively 2 unknowns n and t, rho, p and epsilon. Okay. Now we concentrate on the momentum equation, and we will see that some interesting things can be brought out of that. So first we try to rewrite this advective derivative part, which is v dot nabla v. Now you know there is a very popular identity which simply says that v dot nabla v is equal to gradient of v square by 2 minus v cross curl of v, and curl of v is nothing but our vorticity vector. Okay, so that one we define as vorticity vector. It is called the vorticity vector. Okay, and so this is then simply written to be v dot nabla v is equal to gradient of v square by 2 minus v cross omega. Then the original momentum evolution equation can now be written as del v del t is equal to minus gradient of v square by 2 plus v cross omega minus gradient of p by rho plus g. Okay, so already you can see that this term is rewritten in these two terms. Okay, so for a very simple case where rho is constant, so this gradient of p by rho can simply be written as gradient of p by rho, and then this v square by 2 this gradient of v square by 2 and this gradient of p by rho can be taken under the same umbrella, and this will give you minus gradient of v square by 2 plus p by rho. Okay, so you see, so so for an incompressible fluid, rho is simply a constant, so this is the variable, effective variable is the pressure itself. So you can say that the gradient, if in the momentum evolution equation the gradient part is becomes always as a gradient of a pressure type of thing, then our this term is now having two pressure type of thing. One is the true pressure, this is the true pressure. Another is a type of thing which is v square by 2, which is also a pressure type of thing. Okay, so sometimes you can say this is this is just it's not a true pressure, but this is dynamic pressure or something. Okay, well, there is no hard and fast name for this, but the thing is that the whole thing can be thought to be as an effective pressure type of thing, and this is called as a total pressure, or you can simply write small pt. It's a total pressure. Okay, so of course, once again, so this is the dimension or the unit of this part is not pressure but pressure by density. Okay, so that part you have to be careful, otherwise, so so you can simply say that this is just for the incompressible case, this is effectively a pressure like thing. Okay, so del v del t is equal to minus gradient of something, okay, which is an effective pressure type of thing by this constant density, okay, plus V cross omega plus G, okay. Now V cross omega, or sometimes we can say omega cross V, is called Lamb vector, okay. So this is a name for this vector. This is called Lamb vector. I think I should write like this, Lamb vector. This is the minus of Lamb vector actually, because Lamb vector is traditionally omega cross V, okay. Now if you take the curl of this equation, so this is equation number 1, okay. So if you take the curl of this equation number 1, so that was just a digression for the special case of incompressible fluid. But again, coming back to this original part where rho is a variable itself, okay. And so if we just take the curl on both sides, you will see that this part will be del T of curl of V, okay. Curl means this is like partial space operator, okay, this. So it will always commute with a partial time operator, because space and time, they are not explicitly depending over each other. So del T and curl will be interchanging, okay. Then curl on this term will be vanishing because curl of a gradient is 0. Curl of this term will be there, and curl of this term will simply be something which we will show, and curl of this term will also vanish due to the simple fact that most of the cases these body forces are conservative in nature. So this is seen in nature, the body forces are mostly conservative in nature, and the surface forces are mostly non-conservative, dissipative type of thing. For example, viscous force, when you I mean when I discuss about those things, I will come into more detail. But otherwise, so for example, body force, which is the gravitational force, okay, or the force of gravity basically. So that is a conservative force field. So this conservative force field means for fluid is that the acceleration is having a 0 curl, okay. So and that's exactly what is used here. So you will see, if we just take the curl on both sides, then del omega del T is equal to curl of V cross omega plus curl of rho cross curl of P by rho square. So you just take the curl of this part. There will be two terms. One term will be 0 because curl of gradient of P will be 0. Again, curl of a gradient is 0. The other term where the gradient operator will act on the density, that part will be this one. And this is known as the baroclinic term. This total term is known as the baroclinic term. Now, if the fluid is incompressible, of course, both 2 and 3, okay, then both from 2 and 3, so basically from 2 we have already shown this is a curl. So if you just take the, it's a gradient, so if you take the curl, so this part will be just del omega del T for an incompressible fluid. Once again, this part under a curl will totally go off, okay, and this part will be non-vanishing, this part will vanish. So for an incompressible fluid, from this one or from this one, that is also possible, because gradient of rho is 0 for incompressible fluid, then this is again, this is 0, and you will have this, okay. So you can show that the vorticity vector satisfies this evolution equation, okay. Simple evolution equation, del omega del T is equal to curl of V cross omega, okay. Now that was the case for simple incompressible ideal fluid. Of course, when we are talking about all these things, they are all inside the framework of ideal fluid, because in this part we are only discussing the ideal fluids. We have not at all introduced anything for non-ideal things, okay. So if the fluid is now no longer compressible, no longer incompressible, sorry, but it is compressible, but it is barotropic. What is the meaning of barotropic? So there are two terms which can be confused. One is baroclinic. Baroclinic is this term, okay, and barotropic means that pressure is only a function of density. Pressure is only a function of density, okay. And then you can always write gradient of P is equal to gradient of that function, and which is nothing but f prime. F prime is nothing but the total derivative of f with respect to rho. Okay, so what is this? This is nothing but df d rho gradient of rho. That is the thing, and this df d rho is nothing but this f prime. Okay, so gradient of P can then be written as some function times gradient of rho. Okay, and then of course if you just look the baroclinic term, that is gradient of rho cross gradient of P, and now gradient of P and gradient of rho, they have the same direction because they are parallel. So gradient of rho cross gradient of P will be 0. That simply says that for a barotropic fluid, the baroclinic term is also 0. For an incompressible ideal fluid, baroclinic term is 0. For a barotropic ideal fluid, the baroclinic term is also 0. And if the baroclinic term is 0, then again the vorticity vector satisfies this simple evolution equation. Okay. Another easy but important observation is that for an incompressible fluid, okay, of course, incompressible fluid where rho is constant, the equation of continuity can be written in a very simple form. Okay, so here basically we are trying to show something. So our fluid is basically ideal, and now we are also taking different particular subclasses, for example incompressible, barotropic, etc. And for incompressible ideal fluid, okay, actually here there is no question of ideal or non-ideal, just incompressible fluid. Okay, the equation of continuity can be written as this: del rho del T plus divergence of, there should be a dot sign, yeah, divergence of rho v will be equal to 0, and from that you can say del rho del T is 0 because rho is a constant, v dot nabla rho is also 0 because rho is a constant, so rho times divergence of v is 0, so rho is non-zero, so finally divergence of v is 0. This is an alternative definition of an incompressible flow. Now why we talked about this? Because if we so basically we are just discussing different properties. One property we showed for the vorticity vector and its evolution. Now we will show another interesting property, that is for incompressible fluid. Finally, if we rewrite all the moment equations, then they should look like this: divergence of v is equal to 0, that is the continuity equation. The momentum equation is del v del T is plus v dot nabla v is equal to minus gradient of P plus G, and finally del E del T, del epsilon del T, sorry, plus v dot gradient of epsilon is equal to 0. Why the right hand side is 0? Because if you remember, the right hand side was P times divergence of v, and divergence of v is 0 means this is 0. Okay. Now remember, okay, so in this one we have also used one fact that rho is a constant, so we just say that we are normalizing rho to unity so that rho just don't appear here in order to confuse the reader. So rho is no longer there, rho is there but being a constant, so we just put that constant's value to be 1, and we are saying here that we have, this is the system of dynamical equation which simply have v and p as unknown, and we also have this dynamical equation. Now from your Lagrangian derivative concept you can say this is nothing but del epsilon d epsilon dt is equal to 0. So in an incompressible fluid, basically the three dynamical equations, one is very easy to understand. The third one, that is the internal energy. Okay, the internal energy is constant with internal energy density of a fluid particle is constant with time. Okay, now we have to extract some other interesting information out of this. How to do that? Now we'll take the divergence of the both sides. So beforehand we took the curl. Now we take the divergence of both sides of this momentum equation. Okay, if we do that, first we see again even for divergence there's the same thing like curl. So del t and divergence operator will commute. So that will be 0 plus divergence of this advective term is equal to minus divergence of gradient p is nothing but Laplacian p minus Laplacian p plus divergence of g. Now divergence of g is known, that we know. Now what is not known? This one, this Laplacian p is equal to minus divergence of this. So if this is known, this is nothing but a constant. So we can just, for instance, forget that. And we can say this one is equal to this one. And actually using some mathematical technique, you can always know P in case of V, in case where V is known. Okay. So for an incompressible fluid, P can be determined from the knowledge of the velocity only. Okay. And that's why it is not a isolated thermodynamic, it is still a thermodynamic quantity. That is not a very good way to say. This is not an isolated, or okay, this is not this, I have to say like this. Okay, P is not an independent quantity or variable from V in case of an incompressible flow. Okay, so in some sense you can see that P is, for incompressible flow, P is a function of R and T, but if in case you know V, you know P. Okay, that you can solve. So it simply says, and actually it simply says that in these two equations, practically we have one unknown, and that is the velocity field. Okay, so and that's why we say that in the case of an incompressible fluid, okay, these two equations, they just constitute a dynamical theory themselves. Okay, because this is just a condition, and that's okay. And if you just simply take this equation, so one state variable is V and its evolution equation is given. So 3 scalar unknown and 3 scalar equations. So it's done. So this one does not really participate in the dynamical theory. Okay. So what I just said, the two observations. So for incompressible fluid, what happens? The continuity equation plus the momentum equation make a dynamical theory. The state is only V. Okay. Rho is a state, but rho is a trivial because this is a constant. So it is its evolution equation is there, but this is nothing but d rho dt. Now you see it's a d rho dt or del rho del t. Okay, both are actually 0. Okay, so that's something very interesting to understand. And number B is the energy equation is decoupled and sort of redundant for the dynamical theory. Okay, it's redundant, but this is only redundant when we are talking about incompressible ideal fluids. Now, is it the same case for compressible fluids? Well, of course, the answer is not in general, but well, once again, there is a special family which we already talked about. Okay, and this is the family of the barotropic fluids, where P is a function of rho only. Then again we can write that this momentum evolution equation like this, and this P is nothing but f of rho. So finally we now have again these two equations, but now we have four scalar unknowns. Rho is now a variable and unknown, and three components of velocity, and we have four equations. So again this continuity equation and the momentum evolution equation, they constitute a dynamical theory, but now the state needs two things, rho and v vector. Okay, so the conclusion is both for incompressible and barotropic ideal fluids, dynamical theory can be constituted without the participation of the energy equations. Now why we are talking all about this? So in future, if you do some research or some study in astrophysical systems, for example astrophysical dynamics, the stellar evolution, the equilibrium, the astrophysical turbulence, okay, this type of thing, the star formation problem, then the question is that whether when we start to write the equation, either to do some analytical treatment or to do some numerical works, you have to set the parent equations, the governing equations, and then the question is that can you just do this equation, can you just write two equations like the continuity equation, or simulate mostly, or do some analytical treatment, just continuity equation plus the momentum equation, or you need the energy equation? The answer is, if your system is such that your system is fairly incompressible, then you don't need the third equation, I mean, or the fifth equation, okay, in scalar sense. Or if your system is barotropic, that means you can sufficiently say that, okay, I can think of an isothermal system. So isothermal system is a barotropic system, I will come to that. Or an adiabatic system. Okay, simple adiabatic system, that is another case of a polytropic system. So then actually you are or any other polytropic system. Okay, so if this polytropic assumption, so if, for example, if you draw a profile of pressure with respect to the as a function of the density, and you see that, you can simply see there is a relation, and density on, I mean pressure only varies due to density, then the polytropic relation is a very good approximation for your system, and for that you don't need the third equation. But in several astrophysical problems with important density variation, so that means you cannot consider the incompressible assumption. Okay, for example the star formation problem, for example, okay, often we have to take the energy equation into account when simple polytropic closures cannot be obtained. Okay, cannot be applied or cannot be valid. So that is something, so you understand, that's why I'm saying the modus operandi should be like that. First you have to check whether a polytropic closure is a good approximation for your system or not. So first of all, important density variation, no chance of incompressibility. Second is that you check whether you have like the pressure as a function, as a well-defined function of density only or not. If yes, if you can find, no problem, you just simulate or do analytical treatment just using continuity equation and momentum equation. Otherwise you must include the energy equation. When we are talking the mixing problem in astrophysics, convective problem, okay, convective and instabilities, then of course the energy equation must be taken into account. Okay, for example, I will discuss later about this. So in the next part we will discuss. So that was some discussions about some of the properties of ideal fluids, and we saw actually how we can derive the evolution equation of the vorticity, and also how the dynamical theories or development of dynamical theories are getting simplified in case of incompressible ideal or barotropic ideal fluids. Okay, so that's some I mean, there are so many informations. Now you have to really think, and all these informations are actually very interesting for several circumstances. So these are the general discussions, or the general how to say, exposure of different type of properties of fluids. Now uh, I mean, specifically from case to case, we will just studying the nature of the corresponding fluid, we will try to apply the corresponding property. Okay, that's how it is. So in the next lecture we will discuss about a very interesting theorem, which is also a property of ideal fluid. Of course, it is called the Kelvin vorticity theorem. Okay, thank you very much.